Now coming to the next topic that's quite important, that's called multiplexing. So we now know how we create a signal out of our data stream. We know how to encode, we know how to modulate, but multiplexing is quite important. Why? Well, if you have a line, if you have a wire, for example, that's quite expensive, because if you have Europe on this side and you have the US on the other side, well, you don't want to have a line for each user. That's too expensive. Okay. Or if you have many mobile phones, we don't have a separate space for each of them. So somehow we have to share. So we have to share resources. And the technique for this is called multiplexing. The multiplexing allows us to simultaneously, transmit something over a single physical resource, which is spectrum or the cable. Here in this lecture, we primarily look into two types. It's the frequency division multiplexing. So we subdivide the frequency spectrum into so-called frequency bands, sometimes also called channels, and time division multiplexing. So we subdivide time. And then we can, for example, use this in a round-robin fashion. That's one way. Or we can use this in a random fashion, or whatever you like. Here we will not have a closer look into space division multiplexing, code division multiplexing, polarization, etc. I cover this more in mobile communications course. It's interesting to see when we go up in the layers, we go to layer 2, there we have medium access technologies, and we will see how we combine multiplexing plus a clever algorithm to get multiple access technologies, time division multiple access technologies. There are different schemes for this, also frequency division multiple access technologies. So we combine multiplexing plus a clever algorithm, and the result is this multiple access technologies. But that's a topic for the next chapter, layer 2. So first of all, frequency division multiplexing. What does it mean? So we simultaneously transmit our, in the end, data streams on separate frequency bands. So shown here are, very simple example, these are our classical voice channels, telephone. So we cannot separate humans. So, okay, well, we could do this. So why not using different frequency ranges? For example, children and adults, they have different frequency ranges, and then you can transmit at the same time, and we are able to separate them with our ears. In technical systems, we can say, okay, why not shifting now this channel up to a certain frequency? And the technology doing so, that's modulation. So even in the classical systems, pure analog systems, we could do analog modulations, shifting our baseband channel up to a certain, well, carrier frequency. So, and the thing is, this is very classical, also analog technology, and this can also be used now for digital technologies, and so you can multiplex different voice channels onto this spectrum. So that was one of the ideas, and we can then transmit it. And you know this from everyday life. So these are our classical analog radio stations, where I say, okay, this is at whatever 104.6 megahertz. You have one station, and the other one is 88.8 megahertz, and whatever there is. And this separates different radio stations, because all the radio stations, they use basically, when they create their signal, the same frequencies. So someone speaks, there's music. So this is always something up to, let's say, 20 kilohertz. And then we have to perform the modulation to shift those signals up to the carrier. That's the idea. So frequency division multiplexing. This sounds like, well, really old technology. Yes, indeed. Radio station, radios are quite old technology, a bit more than 100 years now. But even today, we do exactly the same for the highest transmission rates we have, optical transmission. Here we typically speak about so-called wavelength division multiplexing, but you know, if we talk about wavelength or if we talk about frequency, that's the same. So we know that depending on the frequency, we have different wavelengths. So that's very simple. So what we do is we create different wavelengths, different frequencies in our spectrum. Now for wavelengths, here we indicate the wavelength on the x-axis. And we humans, we call this color, so different colors. And we then actually combine this. We combine this and we transmit then over a shared fiber different channels, different colors. So basically all these different colors, different wavelengths, different frequencies, they come together here. You combine them. This can be done optically, so that you don't need any electric component in between. So you transmit many frequencies over this shared fiber, and then you split it and you filter out your frequency. So that's the idea there. So wavelength division multiplexing, used for fiber and fiber optics. And if you use many of these channels, then it's called dense WDM, or simply DWDM, dense wavelength division multiplexing. Okay, so what about time? Time division multiplexing, well, we divide the time domain into time slots. And there are different ways. We can use fixed length. So these are the classical telco systems. So fixed, or variable length, that's classical LAN. And then a time slot of fixed length or variable length then represents a sub-channel. And that's similar to discussion. So you talk to each other and you can have a fixed time slot, so 1 minute each, and you go round robin, or you talk random with random length, but then we know, okay, there must be a coordinator, etc. We'll come back to this in the next chapter when we talk about medium access. But in a simple scheme, we just say there's a channel 1 here, and a channel 2, and a channel 3, and a channel 4, and so on, and so on, and so on, and so on. And then we can assign time slots, that's a time slot here, to a certain user, and we repeat this. And we'd repeat this. And maybe you remember, we said, okay, we sample every 125 microseconds our analog voice signal in the classical digital telephone system and generate 8 bits. And that's enough, these 8 bits, enough to reconstruct our voice signal. So what do we do now? We squeeze in those 8 bits here when we sample them. We only have to make sure that it's our turn every 125 microseconds. So we can squeeze in other users as long as we have our 8 bits every 125 microseconds. And that was basically the core of the transmission of the digital telephone system. It's very, very strict type of multiplexing. So now you have this simple scheme, and we will learn that in local area networks, we can have different schemes. So for example, over time, we have one sender sending something, then the medium may be idle, then it's turn of another one, and then it's idle for a longer time, and then the next one use the medium, and we will see the pros and the cons, what are the problems here, and what do you need in addition? Well, not a big secret, some coordination. So someone has to say who's allowed to send, like in a discussion between people. So classical discussions, so if 2 people speak at the same time, we have a collision, we have a problem. That's a question of the next higher layer, layer 2. Here we're in the physical layer. So we can have time division multiplexing in a very static, fixed scheme, or it can be also a bit more flexible. If you have this fixed scheme, just to show you what you can do, you can now do exactly what I showed you. Okay, why not having a channel in a certain slot? And this has to be repeated, and it's called a frame, and you repeat this every 125 microseconds, because then you can be sure, again, channel 1, channel 2 will show up after this 125 microseconds. Perfect. Okay, we transmit our 8 bits, for example, and then we are happy. And that was the idea. 8 bits per channel, some additional bits, etc., but that's historical, for 125 microseconds, creating a data rate of 1.5 megabit per second. And if you have such a fixed scheme, and this is why the telcos liked it, you can even continue this multiplexing. You can multiplex these streams to the next level, and to the next level, and to the next level, and you can combine them very simple way, because you always pick one from this stream, this stream, this stream, this stream, and them. So it's always round robin. You mix them. You need a higher line speed here, but then you mix the streams, and you see 0, 1, 2, 3, 4, etc., etc., etc. And then again combine, and you can achieve higher and higher and higher data rates. So there are different standards, and this was the classical way of multiplexing. Nice, simple, but not flexible. We'll come back to this when we compare the schemes also on layer 2, but you can imagine this is fine for voice, because if you talk, you generate your 8-bit, and that was the motivation, every 125 microseconds, generating this constant bitrate stream of 64 kilobit per second. Fine. This can be easily multiplexed. But what happens if you click on a web page? Well, or you print something, you have bursty traffic, and then nothing is going on. With these fixed schemes, you cannot reuse the slots for something else, because it's pre-allocated for this specific voice stream. So yes, that's a classical way, but it's not flexible. So this is all phased out, and we go more and more, and we will learn this, how this looks like, to all IP traffic, internet, and for the lower layers, gigabit Ethernet. And there we have versions with 100 gigabit, 400 gigabit Ethernet. So it's pretty high if you compare 400 gigabit Ethernet. But these schemes, they don't have this extreme strict TDM. And here shown an example how you can combine those technologies. Incoming are 48 times 100 gigabit Ethernet and 12 times 400 gigabit, or 12 times 400 gigabit Ethernet. And this can be multiplexed onto fibers with certain wavelengths. You could even combine this on a single fiber, having all these different channels on a single fiber. We come back to these elements. So multiplexing, important scheme to share resources. Think of multiplexing in your everyday life. So where do you see multiplexing if you step out of the door of your house, or even inside the house or on the street, etc.? And what happens if multiplexing goes wrong? What do we need for efficient multiplexing? What do we need for error-free multiplexing? And this also goes together with the advantages of these more fixed or more variable schemes for multiplexing. And I showed you this variable version, well, at least the introduction for time division multiplexing. So what might be a problem if we are quite flexible, more variable for frequency division multiplexing? So radio stations, that was quite fixed. So all the radio stations, they have their carrier frequency. But can we also go variable there? It's possible, but what might be problems?